Good morning, everybody. Welcome to your video lesson for Tuesday, September 11th. This is Mr. Copperthite. I am recording this video for you so you can get a head start on the work that you've been passed out by the substitute today. And I just want to go over a couple of definitions and a couple of conventions and talk about how we can build these formulas for this activity. So we need to start today's lesson with a couple of definitions. Now, I know I have it last on this list on the right here, but the first definition is important to understand is the concept of what's called an arithmetic sequence. Basically, this is a sequence that is consisting of numbers that are a result of adding a number to the previous term. So if you started with 16 and then you add 3, you get 16, 19, 22, 25, etc., etc., etc. There's no change, no variation with how much you're adding by. You also could add negative numbers, which, like subtracting a regular number or adding a negative number. You could do the same thing and accomplish the same goal. Now, as far as expressing these particular sequence rules, we have two ways to do it. We have a recursive formula / recursive rule. And basically, a recursive formula is one that uses the preceding term in a sequence to provide the second term. So the way we note that is as follows. This t sub 1, we read that as t sub 1. This means the first term in a sequence. And that equals a constant value, whatever that value happens to be. The nth term, or let's say, you could say the next term, it really could be the 5th term, the 6th term, or the 20th term, would equal the previous term. So this t sub n minus 1 means, like, if this was the 20th term, we would use the 19th term and add b. We'll call that b our constant of variation on here. Now, so recursive formula work that way, and obviously we'll show a couple of examples of how this works. An explicit formula is also another way that you can express a sequence, but this one's a little more direct. This one here allows you to determine the a specific term in a sequence without having to necessarily write it all out. So an explicit formula basically says, well, let's find out what the first term is. In this case, a would be the first term. This is, by the way, is function notation. So if I wanted the 5th term, I would replace the n with 5. It'd be t of 5. And then you would find that by doing a, the first term, plus b times n minus 1. So if it's the 5th term, this in parentheses would work out to be the 4, and then 4 times the constant variation plus the a would give me my sequence, my term that I'm looking for in my sequence. Now, let me show you a few examples on how this works. So let's say over here we got this sequence over here, 10, 15, 20, 25. So obviously this is a bare bones, super easy arithmetic sequence. You understand right away that the next number is going to be 5 plus 25 or 30, and then 35 and 40 and 45, etc., etc. So for a recursive rule, we have a verbal model first, which in this case is starting at 10 and then increasing by 5 to get the next term. So every time you go to the next term, you just add 5, add 5, add 5, add 5. It's nice and easy. So the way we note that is as follows. So let's using our standard setup here, our first term in the sequence, we just have to identify the first term, which in this case is 10. And then for the recursive rule, whoops, I hit the subscript too quick and dropped the mouse. Let's try that again. There we go. Okay. This case, there we go, t sub n would equal the previous term, oops, and minus 1. I lost the subscript, sorry, and minus 1. Did it again. And minus 1, there it is, 3rd time's the charm, Mr. Copperthite. All right, and then plus, in this case, what are we adding it by? So since we're increasing by 5 every single time to get the next term, we would have our b value be equal to 5 here. So for sequence rules, basically, all we really have to do is just kind of plug into this general format here, and we have to discover what the a and the b are, with a being the first term and b being how much the terms are changing by. So super easy. Now, explicit rule, also not so hard, right? Because we have the same values from our recursive rule. We can easily just plug in that same thing to our rule. So in this case, t of n would equal, our first term is a, so that's 10, plus, and then the second term, 5, and then we just do n minus 1. Now, n minus 1 would stay the same. Now, this is for anything, right? Now, if I had said, hey, what's the 17th term in the sequence, right? Now, instead of having to write out 10, 15, 20, 25, and then have to keep going all the way down to the 17th number, we can just do this. T of 17 equals 10 plus 5 times 17 minus 1, which means that 5 times 17 minus 1, that's 5 times 16, which is 5 times 16 is 110 plus 110, right? I'm just making sure with my math. 16, 18, 16, no, that's not wrong. That's 80, right? 10 plus 80, and then that would equal 90. So the 17th term in the sequence should be 90. So if we follow that rule, basically we can determine, or follow this formula, we can determine any particular number in any particular sequence as long as we know the starting term and how much it varies by. So nice and easy. So our recursive rule, our explicit rules are done for this sequence. Now we'll use the same kind of setup. Let's do a different example. So here we have a sequence that starts here at 6 and then goes to 2 and then goes to -2. And we can see here that if we're going down by the same amount. We're going down by 4 here and then down by 4 here. So our constant variation here is going to be -4, right? So because we're going down. So recursive rule, start at 6, sort of a verbal model, and we can say add -4 to get the next term. Right, so that's sort of the in-words version of this. Now, the recursive rule is as follows. Our first term, which is our a value, which we'll also use in the explicit rule, is 6. Then to get our next term, we're going to do t of n equals the previous term, n minus 1, plus -4. Now we could write -4 there, but I'm just trying to be consistent here with the way this format works. We could write t sub n minus 1 minus 4, and we still get the same result. Explicit rule, same deal. We already found our a, we found our b, so we just have to write the function notation. So t of n equals, our a value is 6 plus our constant variation, which is -4, and then n minus 1. And again, just like before, if I wanted to find a certain term in a sequence, I can do that. So let's say for this one, let's say I wanted to find the 10th term, right? So I would do t of 10, and that equals 6 plus -4 times 10 minus 1. 10 minus 1, excuse me. I can give the answer right there. So that simplifies to 9. So that's 6 plus -4 times 9, or just 9 in parentheses like that. That equals 6 plus -36, or -30. Right? So that works out to be, so if I wanted the 10th term of the sequence, if I continued this sequence all the way up through the 10th term should be -30. So that's that. So it's recursive rule, explicit rules, you'll get the hang of it. The new thing for you is seeing that you're basically coming up with a formula based on a sequence, and that's going to be a very important skill for algebra, is being able to take things like data points and coordinates and turning them into formulas for general representation, which will allow you to find and predict values that are far higher or far beyond the scope of the work that you would have to do, because otherwise you'd have to write out the next term, and the next term, and the next term, and the next term. Well, or you can just use this nice formula right here, and boom, there's your 10th term. Okay, now for this last part of the slideshow here, I've got, as you can see, I've already kind of made a little bit of information on the graph here. This particular exercise calls for you to make some measurements about paper cups. Now, of course, I'm providing this information to you because of the fact that I'm not here for us to get some cups and to kind of do it ourselves, and that's okay. We can standardize this and get ourselves some nice and consistent values here. So I've got on here the height of a paper cup, standard paper cup that's 8 ounces in capacity, in centimeters, is 8.9 centimeters. Now, if I were to put another cup inside of here, remember these paper cups are tapered in the fact that you could basically nest them together. You can put multiple paper cups in here and come around with a stack of paper cups and pull them out as you need, right? So a single paper cup, obviously, much higher. But if you stack them and then measure the height of the stack, you'll see that the stack height only increases a little bit. In this case, it's only increasing by ½ centimeter, 8.9 to 9.4 to 9.9, and so forth and so on. Now, if I graph that data, if I go by 2's on my x-axis and 2 on my y-axis and 1 on my x-axis, you can see that the graph is sort of linear, right? It starts off with a value here, since we're going by 2's here, which is a little bit less than 9, 9.4, 9.9, all the way up. So if we continued this pattern, this line would basically kind of look like this, right? Now, obviously, we shouldn't put a line here, but I just want to show you that they are in line, right? We shouldn't put a line here because, again, this is a discrete graph. We can't have half a cup. Well, half of a paper cup. Well, we could, I guess. It would still be a cup, but it wouldn't have the same capacity. All right, but I digress. Now, the rule that fits this pattern, we can say recursively or explicitly as follows. So over here on the right, you can see we've got a recursive verbal model here. So that's starting at 8.9 and increasing by 0.5. And then here I've got a recursive model. Now, the first term, with 1 cup in this case, is 8.9. The next term is found by adding 0.5 to the previous term. So there again is our recursive formula. For our explicit formula, we take those same two values, the 8.9 and the 0.5, and we just plug them into this function setup right here. So this here is t of n equals 8.9 plus 0.5 to the n minus 1. Now, as a last example, what if I wanted to know how tall 100 of these paper cups would be? Well, if I do this, if I go 8.9 plus 0.5 times n minus 1, which in this case is 100 minus 1, right? This simplifies as follows. 8.9 stays here, and if I use my order of operations, this is going to be 99, 0.5 times 99, right? Which is going to be 49.5. 8.9 plus 49.5, and then if this simplifies here, this is going to be 58.4, right? 58.4. Okay, so that works out. Yeah, that works perfectly. So that means that if I stacked 100 paper cups on top of each other, it would be 58.4 centimeters tall. Okay, or or a little more than half a meter. Right, so that works out nicely. So there's your lesson on explicit recursive formulas. This is sort of the first page of the activity, but you'll see that there's more to do, obviously, with this. Go ahead and work on it, and as you go through it, if you need to go back and see some definitions and look through the examples again, hopefully you also copied some of this into your notebooks, because that will be helpful, especially if there's going to be a quiz on Friday, which there is. All right, so anyway, I hope that you found this lesson helpful. Make sure to email me any questions you have or comment below in this video. Have a great rest of your day.